All right, problem 2. So we've got a water tank. It's shaped of an inverted circular cone. Went ahead and sketched it here. It's a base of radius 6 feet and total depth of 8 feet. So we can go ahead and sketch that. So the base radius is 6, and then the total depth of this tank is 8 feet. Okay, and then we're pumping water into the tank at a constant instantaneous rate of 4 cubic feet per minute. That's super important, right? That's the change in the volume. The volume of water in the tank is increasing. It's changing at a constant rate of 4 cubic feet per minute. So we can go ahead and write that down. Maybe we'll highlight that. Let's see here. Yeah, water's being pumped into the tank at 4 cubic feet per minute. And so we can go ahead and say, okay, I don't know what this problem is asking, but I know that dV dt, the volume of the tank, is always 4. It's a constant 4. So then we're asked to find, I'll always use pink to mark that, find the instantaneous rate at which the water level is rising. And then it tells me when the water is 3 feet deep. So let's summarize what this is actually saying. This is saying that our goal is to find the instantaneous rate of the water level rising. That's dH dt. If I let h represent the height of the water here, then I want to find dH dt the moment that the height is 3 feet. And so the first part of the problem is just thinking about what you've been told, sketching a picture, thinking about what you've been told. Okay, so I need some relationships, often more than one. And so somehow, first off, when I think about the formula for the volume of water in this tank, I can write that down. Hopefully you know the volume of a cone. You should get V is 1/3 pi r squared h. Now you are absolutely allowed to panic slightly because our formula has 3 variables involved, right? I've got V and then I've got both R and H. I really don't like that. I'm going to get rid of the V when I take derivatives because it's just going to give me dV dt, and that's a constant of 4. But I don't want both of these variables over here. And so looking at a second relationship between R and H, I realize, look, there's this triangle thing going on, right? This triangle is 8 and this is 6. And it's similar to this triangle with R and H. And so you know that with similar triangles, let's just say it like this. We'll say similar triangles imply that R over H is equal to 6 over 8. Clean that up. So now you can say, so R is 3H over 4. Okay? So now at this point, I'm going to go ahead and I'm going to plug this relationship into that relationship. Everywhere I see an R, I'm going to replace R with 3H over 4. And so I get that V is equal to 1/3 times pi. Instead of R, I'm going to write 3H over 4 squared times H. Now I'm going to clean that up a little bit. I get V is, let's see, when I square out the 3's, I'm going to cancel one. So I'm going to get a 3 pi h cubed all over 4 squared, which is 16. So I get a 3 pi h cubed over 16. That's my volume. Okay, at this point, I'm in really good shape. So my goal is to find dH dt. I've got my formula entirely in terms of h. That brings up a great question is, how did what I solved R over H here, I could have solved for H in terms of R. And if I did that, then this formula wouldn't have any H's in it. It would only have R's in it. You could figure out the rate of change of dr dt and then go back and plug it in and take derivatives here. You can do that. But it's easiest if you know that you want dH dt to get your formula in terms of the H's, not in terms of the R's. And so I've done that. So now at this point, this is step 1. I figured out my different relationships. Now I'm going to compute dV dt. And on this side, I just get dV dt. On the other side, I get what? 3 times 3 is, 3 times 3 is 9 pi h squared times dH dt all over 16. All right. And at this point, I want to go ahead and think about what I know. I know dV dt, we were told water's coming in at a constant rate of 4. So I'm going to move the 16 over. This is just 4, so I get 64 is 9 pi h squared dH dt. So I get that dH dt is 64 over 9 pi h squared. And so now I realize, okay, I don't just want dH dt. I want dH dt the moment when the height is 3. The height of the water is 3. And so I can say, well, dH dt when the height of the water is 3 is equal to, let's think really carefully together, what? So 3 squared is 9. 9 times 9 is 81. So I'm going to get 64 over 81 pi. And that's the rate of change of the height of the water at the instant when the height of the water is 3. And of course, let's think about it together. Is the height changing faster or slower the higher it gets? Think about that. Maybe pause the video and see if you can answer that question. Hopefully you see that the higher the water gets, the slower the height actually changes, because there's more to fill up, right? It's going to be changing slower and slower the higher the height gets. Look at your formula and realize that as h gets bigger, this number gets smaller. So you can see the h's here. Think about the limit as h goes to infinity. It's going to pull this whole thing towards 0, actually. And so you can see that change happening here. Of course, our tank, h can't go to infinity in our situation, but nonetheless, you can see what's happening. All right, so that's the second example. 2 more to go. We'll pause, we'll end this video and go on to the next one.